Okay, so um, this problem says a commuter backs her car out of her garage with an acceleration of 1.4 meters per second square. How long does it take her to reach a speed of 2 meters per second? Okay. So there's the acceleration, and we'll make our axis point that way. Okay. Oftentimes I won't draw the axes, but from the sign you can tell which way the axis is pointing. Is 1.4 meters per second square. So they're asking you how long does it take to reach this final velocity. The initial velocity was 0. You started off in the garage at rest. Okay. So T is V minus V naught divided by A. Okay. And your final velocity is 2 meters per second. Okay. So it's positive. Initial velocity was 0. So 2 meters per second divided by 1.4 meters per second squared. Okay. And you'll get meters per second will cancel with meters per second, and once a second will come up there. So this is 2 over okay, so 1.43 seconds. Okay. Now part B says if she then brakes to a stop in 0.8 seconds, what is her acceleration? Okay. Now, so she's going at 2 meters per second, and then she sees something and she's got to stop real fast. Okay. So final velocity is initial velocity. This time they give you the final velocity. Your initial velocity is 2 meters per second, and they give you the stopping time, and you got to calculate the acceleration. This time the final velocity is 0. Okay. The initial velocity was 2 meters per second, and the stopping time was 8 seconds. And this works out to 2.5 meters per second squared. The negative, so in part B, so here was the initial velocity, here was the final velocity, so the acceleration was pointing in this direction, and that direction was positive, the acceleration was pointing in the opposite direction, and that's the negative sign. Okay. Now here's what I want you to notice. When she was starting to move and speeding up, her acceleration was that 1.4 meters per second squared. That's what the engine provided. Look at the stopping acceleration. The magnitude of the stopping acceleration is larger than that, and this is always the case. Okay, in most instances in devices that we use. Why is that? This is a safety issue. Okay, so you pull all stops to stop. Okay, you put brakes on all 4 wheels and stuff like that. Okay, you can, if you're super rich, you can buy, this is very expensive. You want this number to be bigger, for this to go from 1.4 to 1.8 meters per second squared, it's going to cost you a chunk of money. All right, so you can see this in trucks, trains, and stuff like that. So this is a safety issue. Okay. All right, we'll do one part on this one. Okay, so a particle has a constant acceleration of 6 meters per second square. If its initial velocity is 2 meters, at what time is its displacement 5 meters? Okay, so x minus x naught, that's the displacement, equal to v naught t plus 1/2 at squared. Okay, so you want this to be displacement, initial velocity is 2 meters, and now I'm not going to write units, we are always working on SI units, 6t squared, okay, and you want this to be 5 meters. Okay, so you want to solve this quadratic equation. Okay, and you guys know the roots of the quadratic equation are okay. That is, this equation has two solutions, and those are the two solutions. Okay, so t equal to -2 plus or minus 2 squared minus 4, 3 times minus 5 divided by 2 times 3. So the two solutions are -2 plus or minus, and this is 4, that's 12, 60, 64, root of 64 is 8, divided by 6. So plus 6 divided by 6, 1 second, and minus 10 divided by 6 is minus 1.67 seconds. So those are the two solutions. Okay. Now, so of course this solution is, the positive time solution is you're moving forward, so there you'll have moved 5 meters. Okay. All right, what is the negative time solution? Okay, the negative time solution is let's see. All right, I can't think of what the negative time solution means right now. Okay, anyway, this is the solution you want. Okay. All right. Velocity is easy, so I'll let you guys calculate that yourself. Okay. Velocity is just, part B is just v equal to v naught plus at. And so you just put 1 second for that. All right. So the next problem is, freight trains can produce only relatively small accelerations. What is the final velocity of a freight train that accelerates at a rate of 0.05 meters per second squared? Okay, 0.05 meters, so this is about 5 centimeters per second. So the velocity of a train is increasing by about 2 inches per second per second. Okay, that's the acceleration. Okay. For 8 minutes, starting with an initial velocity of 4 meters per second. Okay, so what is the final velocity of a freight train? Okay, for part A, final velocity is initial velocity plus acceleration times time. Okay, so final velocity is 4 meters per second plus acceleration is 0.05 meters per second square. times 8 minutes. 8 minutes is that many seconds. Okay. So it takes the train a long time to get up to speed. So 28 meters per second. Yeah. That's the final velocity. And again, like I said, 10 meters per second is roughly 25 miles an hour. So this is going at about 75 miles an hour. Okay. Now it says if the train can slow down at a rate of 0.55 meters per second square. So you see the acceleration, speeding acceleration is 0.05, and the braking acceleration, deceleration is about 11 times greater. Okay, and again, force is equal to mass times acceleration. So to stop, you're working 11 times harder. Okay. Again, so the braking acceleration is that. If the train can slow down at a rate of that, how long will it take to come to stop with this from this velocity? So now this is your initial velocity. How long will it come and take to stop? And again, you multiply the acceleration by a factor of 10. The time taken will decrease by a factor of 10. Okay? Except that in this case, you're stopping from 28 meters per second to 0. This 8 minutes was accelerating from here to there, but your acceleration is different as well. Okay. All right, so how long will it take to stop? V equal to V naught plus AT. So in this case, again, T is again V minus V naught divided by A. Your final velocity is 0. Your initial velocity is 28 meters per second. Again. And your acceleration, so you were traveling, you were traveling in this direction, okay. And if you're braking, your acceleration is in that direction, and it's negative 0.55 meters per second squared. Okay, meters per second will cancel, and you'll be left with a second, and that'll come up there. And this is 0.85 minutes. Okay, so again, roughly the acceleration was 10 times bigger, and the stopping time is 10 times smaller. Okay. How far will the train travel in each case? Okay, so part C. Okay, so we'll call this D1 and D2. So this is the distance traveled during acceleration, and that's the distance traveled during deceleration. Okay, so this is all right, so x minus x naught for part 1, okay, D1, we'll call it. This is D1 equal to 4 meters per second. And how long were you accelerating? 8 minutes, which was 480 seconds. What was the acceleration? 0.05 meters per second square, 480 seconds. So about 8 kilometers from here to roughly State Road 40. Okay, here to Ormond Beach. Okay, so similarly you can calculate D2. Now, what was your braking distance? Okay. Okay, let's see. I have the braking time, but let me calculate it a different way. Okay, and so we'll calculate it this way. This will be our braking distance. And the reason I've done this is the following. So this is your initial velocity. The train is going at 28 meters per second, and you want to stop the train. Okay, so you see, this is the distance over which you stop. The greater your acceleration, the smaller your stopping distance. Okay, now you guys might not remember this. Most of you guys have not driven a car without anti-locking braking system. Okay, so in the old days, they used to ask, does your car have an anti-locking braking system? You know, what's that?
I guess that'd be
Okay, so you have a car without an anti-locking. Yeah. So what this is the rolling friction when you lock your car, when you brake your car, then the brakes lock, then you're sliding, the car is sliding. And that takes a longer distance to stop. That's because the acceleration is smaller. Okay. If your car keeps rolling, it provides a greater acceleration, your stopping distance is smaller. You know? And your insurance rates are lower. All right, so again, so that's the point. Greater your acceleration, greater your braking accelerations, smaller your stopping distance. Okay? And of course, if you slide on a rainy day, the friction is even smaller, the acceleration is even smaller, and your stopping distance is greater. All right, so this is 0. Your initial velocity is 28 meters per second. Plus your acceleration is negative 0.55 meters per second square. So x minus x naught is as negative 28 square divided by 2 times negative 0.55. So this is your stopping distance. Okay, so you can see this. Okay, your acceleration distance was 8 kilometers, and your stopping distance is 0.7 kilometers. Okay, you see the stopping acceleration was 10 times greater, and the stopping distance is 10 times greater, less. Okay. There's one case where the braking acceleration is the same as the stopping acceleration. I mean the speeding acceleration in your boats. You can't have a bigger, greater stopping acceleration. Okay? So you gotta plan your stop more carefully, especially if you're driving big boats like ships. Okay. All right. Let's say somebody jumps off the top of a building and the sidewalk stops them. That hurts. What's that? Yeah. On the other hand, you jump off from the same building and a bunch of mattresses stop you. That doesn't hurt as much. What was the difference? What?
You're alive.
Yeah, you're right. Yeah, what is technically the difference?
The negative acceleration is less extreme.
Yeah, so what it is large accelerations are bad for you. Okay, so that's what your airbags do. If you get into a wreck and your steering wheel stops you, you experience large accelerations. That's like hitting the sidewalk. Okay? And an airbag stops you, your acceleration is not as large. Okay? So all your safety devices, what they are decreasing the acceleration. Okay? And we'll see how nature solves this problem. Okay. So woodpecker's brain is specially protected from large accelerations. So you see, that's what you want to do. You want to avoid large accelerations. Okay? By tendon-like attachments inside the skull. Okay, so what this is okay, our brains are cushioned by a layer of fluid. Okay, and if let's say I hit the wall, okay, and so I go to, let's say I'm going at 10 miles an hour, my brain is going at 10 miles an hour, my skull hits the board, my skull stopped, the brain is still traveling at 10 miles an hour. Okay, and then if the fluid is not up to the task of cushioning, my brain hits my skull, I get a headache and all that kind of stuff. Okay, so here's a woodpecker. It's doing this on purpose hundreds of times. It's looking for little grubs in the tree or whatever it is doing. Okay. It goes there and the beak gets stopped. If the brain hits the skull, it'll be flying around with a concussion all its life. So how do you prevent that? Okay? So here's what nature does. Here's the brain. It might have fluids. In addition, it has rubber bands. Okay. So as this brain travels, this rubber band stretches and pulls the brain back. Okay. So that's the airbags for the woodpecker. Okay. So that's what this problem is about. Okay. So woodpecker's brain is specially protected from large accelerations. Again, you want to avoid large accelerations. Okay. Why do you want to avoid large accelerations? If the acceleration you experience is small, then the forces that come into play are smaller, okay, causing less damage. All right. So by tendon-like attachments inside the skull, so the brain is attached by these rubber bands inside the skull, okay. The woodpecker's head comes to stop from an initial velocity of 0.6 meters per second in a distance of only 2 millimeters. So when it's pecking, it's going at 0.6 meters per second, and the stopping distance is 2 millimeters. Okay. Find the acceleration in meters per second square and multiples of g. So v equal to v naught plus a. Oops, no, we want this equation. Okay, so the stopping distance for the skull, for the head, is 2 millimeters. The initial velocity was 6.6 meters per second square. The final velocity is 0. Okay, and so we'll find the acceleration. So the acceleration is v square minus v naught square divided by 2 times x minus x naught. 0 minus 0.6 2 divided by 2 millimeter, and a millimeter is 1,000th of a meter. Okay. So this works out to so again, that's 0.36. Negative sign just tells you 0.36 divided by 4 into 10 minus 3. That's 360 divided by 490, minus 90 meters per second square. Okay. So so that's the acceleration. Head comes to a stop. Find the acceleration of the skull. Okay, so and that's that. And okay, so what you want to do is you want to get in the habit of doing this. So that's a number, minus 90 meters per second square. And I want you to give this acceleration in terms of g's. What that means is, okay, so what I'm going to do is I'm going to multiply this by, what is this? This is 1. G divided by that, that's 1. And so I'm going to give this in terms of g's. 90 divided by that, the meters per second square cancel. Okay, why do we calculate this? Okay, the force, so the stopping force on the head is mass times the acceleration, mass of the head times the acceleration, which is mass times 9.2 g's, 9.2 mg. That is the weight of the head. The stopping force is 9 times the weight of the head. And that's why we solve it like that, write it in terms of g's. Okay? So if you're experiencing a force of 10 g's, okay, the stopping force is 10 times your body weight. Okay? And it turns out that 20 Gs are bad for your health. Okay? All right. Okay, so now we'll do part C, calculate the stopping time, but we won't do that. The tendons cradling the brain stretch, making its stopping distance 4.5 millimeters. Okay, so even before we calculate this, let's look at this equation. So the brain was also going at 0.6 meters per second. The head stopped in 2 millimeters, but the brain stops in 4.5 millimeters because these guys stretch and there's more than a 2 millimeter gap there. Okay, so let's say there's a 3 millimeter gap. So the stopping distance increased. The stopping distance increased, it's doubled, so the acceleration will be half as much. Okay, so the brain itself will experience accelerations of about 4 Gs. Okay, and apparently the woodpecker can withstand millions of those Gs. I mean, those Gs millions of times because it's pecking millions of times over its lifetime without getting a concussion. Do you guys understand that? Okay, so, all right. So like I said, nature knows physics. Yeah. So now we'll calculate for the brain. And again, I've not written down all units and stuff like that, but okay. So 4 Gs, even with the rubber bands, it's experiencing 4 Gs. But apparently that's good enough. Yeah. All right, we'll skip this one. There should be a recording of that. Okay. You guys don't feel rushed, do you? Okay. Because I have enough time to solve 3 more problems, okay? So this problem says you throw a ball straight up with an initial velocity of 15 meters per second. It passes a tree branch on the way up to a height of 7 meters. How much additional time elapses before the ball passes the tree branch on the way down? Okay, so here's the tree branch. Here's the tree branch. You throw the ball up with a this was 7 meters. You want to calculate the time spent above the tree branch. Okay. So now we haven't proved this, but okay. if something is traveling under the influence of gravity alone, if it's going at 15 meters per second, when it comes back to the same spot, it's going at minus 15 meters per second. Okay. All right, so what we'll do is we'll calculate the velocity there, and then at this point it'll have the same velocity, same magnitude, and the velocity will be in the opposite direction. Okay. And then we'll use that to calculate this time. All right, so part 1. Its initial velocity is 15 meters per second. It travels 7 meters, and let's calculate the final velocity. So again, v square equal to v naught square plus 2a x minus x naught. So v square is, v is initial velocity is 15 meters per second. And again, I'm not writing. Acceleration is in the opposite direction, so it's minus 9.8 meters per second square. And the distance traveled is 7 meters. Okay. Okay, so what we have calculated is when the ball starts off at 15 meters per second, and after traveling 7 meters, to 7 meters is a little higher than this ceiling. Okay. This ceiling is about 5 meters, okay, from the ground. So a little higher than that. It slowed down to 9.4 meters. Okay. Now for part 2, it starts off at 9.4 meters. And its final velocity will be in minus 9.4 meters. Okay? And we'll calculate how much time it spends above the tree branch. So since we need time, this is the equation we'll use. Okay. The final velocity is that, negative 9.37 meters per second. Oops. Initial velocity is plus 9.37 meters. And acceleration is negative 9.8 meters per second squared. So it spends roughly 1.9 seconds above the tree. Okay. All right. So let's see what this problem says. Between t equal to 0 and t equal to t naught, a rocket moves straight upward with an acceleration given by that. So here's Here's a problem where the acceleration is not constant. Okay. It's a function of time where a and b are constants. By the way, so acceleration is has dimensions of length over time square. It's meter. Okay, SI units would be meters per second square. So this guy would be in meters per second square. A has units of meters per second square. B has units of meters per second square plus 1/2, because then that 1/2 second to the 1/2 will cancel that. So B has units of meters per second to the power 5/2. Okay. Again, if x is in meters and t is in seconds, what are the units of A and B? Okay, so again, units of A are meters per second square and B are meters per second square plus 1/2. Okay. If the rocket starts from rest, how does the velocity vary with time? Okay. So in part B, again, if you look at your notes, velocity, change in velocity is given by this function. Okay. So what this is velocity at t naught minus velocity at 0. Okay. It starts from rest, so this guy is 0. Okay. So essentially you're getting velocity as a function of time by doing that integral. Okay. So let's do that integral. Okay, so we have v as a function of time given by this. Okay. What we are doing in this problem is, so what you have learned is, so if you have, okay, we'll keep it simple. So what you're seeing in this problem is, if you take a derivative, take a time derivative, you go from position to velocity and velocity to acceleration. In this problem, we are coming backwards, and what you have to do is you have to integrate. That's all. Okay. So we are showing you the inverse process. Okay. Okay, so if the rocket starts from rest, how does the velocity? If the initial position is 0, what is the rocket's position as a function of time during the same interval? Okay, so part C, again, look up your notes. The displacement is given by okay, so x of t naught minus x of 0 they tell you start at the origin, so that's 0. So x as a function of time is 0 to t naught a t minus 2/3 b t to the power 3/2. So x as a function of time is a by 2t square minus 4/15 b t to the power 5 halves. So what we did was, in this problem, you were given that, and via doing by an integration you got velocity, and doing another integration you got x. Okay. So this time, okay, so when you have a rocket, you know what kind of acceleration you'll provide to the rocket, and you can, doing by integration, you'll know that after the rocket has burned 8 minutes, that's where you'll end up. Okay. All right. Okay, one last problem. So a hot air balloon rises from ground level at a constant velocity of 3 meters per second. 1 minute after liftoff, a sandbag is dropped accidentally from the balloon. Calculate the time it takes for the sandbag to reach the ground. Okay, and the velocity. We'll just do part one. Okay, so this is ground level, and it starts off at 3 meters per second. So 1 minute later is 60 seconds. In 60 seconds, well, it was going at constant velocity, 3 meters per second. 3 times that is, it's 180 meters up. Okay. And now a sandbag is dropped accidentally from the balloon. Okay, so you drop a sandbag. Okay, so what is the velocity of the sandbag?
The one that's dropped?
Mm-hmm.
0.
Okay. So let's say you're driving on I-95 at 80 miles an hour. You roll down your window and drop an apple.
So in this case, it would be 3 meters.
Very good. Okay. So you drop, it's moving at 3 meters per second. And so the sandbag will rise up and then fall down. Okay. Now see, once it's dropped, it's moving under the influence of gravity, and its acceleration is 9.8 meters per second square downward. Okay. The time it takes for the sandbag to reach the ground. Okay, so the sandbag was dropped from a height of 180 meters, and so okay, so our x-axis is this way. X naught is 180. Well, okay, so we'll do x minus x naught equal to v naught t plus 1/2 at squared. Okay, our axis was pointing that way. Final x is 0 meters. Initial x is 180 meters. Initial velocity is 3 meters per second plus 1/2 negative 9.8 meters per second squared t squared. Okay, so minus 180 meters, 3t minus 4.9 t squared. I'm not writing units because it gets messy. So 4.9 t squared minus 3t minus 180 equal to 0.
Plus 180?
No, I brought this.
Oh, I see. Never mind.
Yeah. Okay. All right, so again, the roots of the equation are, so t is 3 plus or minus minus 3 square minus 4 AC minus 180 divided by 2 point. Okay. Okay, so that's the answer. What is this answer? Okay, so what we have solved is this is the final position, and all right. Okay, what that negative time tells you is, so if you had thrown the ball, like if you had thrown the sandbag from this point, from the ground level, and it would have gone a parabolic trajectory, you would have had to throw it at minus 5.8 seconds ago for it to reach there. Okay, and then it takes 6.4 seconds to land to the ground. That's what the negative solution is. Yep.
Could you assume that it took 5.7 seconds to get up to that point?
Yeah, that's what that is. Yeah. So if you throw the sandbag at an appropriate velocity, that's what that solution is. Okay. All right, guys, so we'll stop here. Okay.